Hi, I am Anthony Guiller Lumanglas, presenting Chapter 11, The Transmission of Binary Data in Communication Systems. The topics covered in Chapter 11 are digital codes, principles of digital transmission, transmission efficiency, and basic modem concepts. The proliferation of applications that send digital data over communication channels has resulted in the need for efficient methods of transmission, conversion, and reception of digital data. Data processed and stored by computers can be numerical or text. The signals used to represent computerized data are digital rather than analog. Even before the advent of computers, digital codes were used to represent data. Early digital codes. The first digital code was created by the inventor of the telegraph, Samuel Morse. The Morse code was originally designed for wired telegraph communication but was later adapted for radio communication. It consists of series of dots and dashes that represent letters of the alphabet, numbers, and punctuation marks. The earliest radio communication was also carried out by using the Morse code of dots and dashes to send messages. A hand-operated telegraph key turned the carrier of a transmitter off and on to produce the dots and dashes. These were detected at the receiver and mentally converted by an operator back to the letters and numbers making up the message. This type of radio communication is known as continuous wave transmission. Another early binary data code was the Bodo code. Used in the early teletype machine, a device for sending and receiving coded signals over a communication link. With teletype machines, it was no longer necessary for operators to learn Morse code. Whenever a key on a typewriter's keyboard is pressed, a unique code is generated and transmitted to the receiving machine, which recognizes then prints the corresponding letter, number, or symbol. This is an example of a Morse code. As you can see, a Morse code consists of series of dots and dashes that represents letters of the alphabet, numbers, and punctuation marks. The next one is the modern binary codes. For modern data communication, information is transmitted by using a system in which the numbers and letters to be represented are coded, usually by the way of a keyboard, and the binary word representing each character is stored in a computer memory. The message can also be stored on a magnetic tape or disk. The following sections describe some widely used codes for transmission of digitalized data. The first section is the American Standard Code for Information Interchange. The most widely used data communication code is the 7-bit binary code known as the American Standard Code for Information Interchange, or ASCII, which represent 128 numbers, letters, and punctuation marks, and other symbols with ASCII. A sufficient number of code combinations is available to represent both uppercase and lowercase letters of the alphabet. The first ASCII codes have 2 to 3 letter designations. These codes initiate operations or provide responses for inquiries. The other one is the hexadecimal values. Binary codes are often expressed by using their hexadecimal rather than decimal values. To convert binary code to its hexadecimal equivalent, first, divide the code into 4-bit groups, starting at the least significant bit on the right and working on the left, assuming a leading zero of each codes. The next one is the extended binary coded decimal interchange code. The extended binary coded decimal interchange code, or EBCDIC, pronounced as EBCDIC, developed by IBM, is an 8-bit code similar to ASCII, allowing a maximum of 256 characters to be represented. Its primary use is in IBM and IBM-compatible computing systems and equipment. It is not as widely used as ASCII. The next topic is the principles of digital transmission. Serial transmission. Data can be transmitted in two ways. The first one is the serial, and the second is the parallel. Parallel data transmission is not practical for long-distance communication. In a serial transmission, each bit of a word is transmitted one after another. This figure represents serial transmission. Data transfers in a long-distance communication systems are made serially, and each bit of a word is transmitted one after another. This figure shows that the ASCII form for the letter M being transmitted one bit at a time. The LSB is transmitted first, and the MSB last. The MSB on the right indicating that it was transmitted later in time. Each bit is transmitted for a fixed interval of time t. The voltage level representing each bit appear on a single data line one after another until the entire word has been transmitted. For example, the bit interval may be 10 microseconds, which means that the voltage level for each bit in the word appears for 10 microseconds. It would take, therefore, 70 microseconds to transmit a 7-bit ASCII word. Serial transmission, expressing the serial data rate. The speed of data transfer is usually indicated as the number of bits per second. Another term to express the data speed in digital communication systems is baud rate. Baud rate is the number of signaling elements or symbols that occur in a given unit of time. A signaling element is simply some change in the binary signal transmitted. Asynchronous transmission. In asynchronous transmission, each data word is accompanied by start and stop bits that indicate the beginning and the ending of the word. In data communication terminology, this high level is referred to as mark. Most low-speed digital transmission is asynchronous. This technique is extremely reliable, and the start and stop bits ensure that the sending and receiving circuits remain in step with each other. In this diagram, the start bit has become the same direction as all other bits in the data word. The transmission from mark to space indicates the beginning of the word and allows the receiving circuits to prepare themselves for the reception of the remainder of the bits. Synchronous transmission. The technique of transmitting each data word one after another without start and stop bits, usually in multi-word blocks, is referred to as synchronous data transmission. To maintain synchronization between transmitter and receiver, A group of synchronization bits is placed at the beginning of the block and the end of the block. Synchronous transmission assumes that the receiver knows or has a clock frequency identical to that of the transmitter clock. Usually, the clock at the receiver is derived from the received signal, so that it is precisely the same frequency as, and in synchronization with, the transmitter clock. In this figure, figure 11.8 shows one arrangement. Each block of data can represent hundreds or even thousands of 1-bit characters. At the beginning of each block is a unique series of bits that identifies the beginning of the block. Two 8-bit synchronous or SYN codes signal the start of the transmission. Once the receiving equipment finds these characters, it begins to receive continuous data. The block of sequential 8-bit words or bits. At the end of the block, another special ASCII code character, ETX, signals the end of transmission. The receiving equipment looks for the ETX code. Detection of this code is how the receiving circuit recognizes the end of the transmission. An error detection code usually appears at the very end of the transmission. Encoding methods. Whether digital signals are being transmitted by baseband methods or broadband methods, before data is put on the medium, it is usually encoded in some way to make it compatible with the medium, or to facilitate some desired operation connected with the transmission. Transmission efficiency. Transmission efficiency is the accuracy and speed with which information, whether it is video or voice, analog or digital, is sent and received over communication media. It is the basic subject matter of the field of information theory. Hartley's law. The amount of information that can be sent in a given transmission is dependent on the bandwidth of the communication channel and the duration of transmission. Mathematically, the Hartley's law is C is equals to 2B, where the C is the channel capacity and B is the channel bandwidth. Transmission media and bandwidth. The two most common types of media used in data communication are wire cable and radio. The two types of wire cable used are coaxial and twisted pair. Coaxial cable has a center conductor surrounded by an insulator over which is a braided shield. The entire cable is covered with a plastic insulation. A twisted pair cable is two insulated wires twisted together. This is a figure of the types of cable used for data transmission. A is the coaxial cable, B is the twisted pair cable, unshielded UTP. A twisted pair cable is a two insulated wires twisted together. The one shown in figure 1110 is an unshielded twisted pair, or UTP cable, but a shielded version is also available. Coaxial cable and shielded twisted pair cables are usually preferred, as they provide some information from noise and crosstalk. Crosstalk is the undesired transfer of signals from one shielded cable to another adjacent one caused by inductive or capacitive coupling. The bandwidth of any cable is determined by its physical characteristics. All wire cables act as low-pass filters because they are made up of the wire that has inductance, capacitance, and resistance. The upper cut-off frequency of a cable depends on the cable type, its conductance and capacitance per foot, its length, the sizes of the conductor, and the type of insulations. Coaxial cables have a wide usable bandwidth, ranging from 200 to 300 MHz for smaller cables to 500 MHz to 3 GHz for larger cables. The bandwidth decreases drastically with length. Multiple coding levels. Channel capacity can be modified by using multiple level encoding schemes that permit more bits per symbol to be transmitted. Remember that it is possible to transmit data using symbols that represent one more than just one bit. Impact of the noise in the channel. Another important aspect of information theory is the impact of noise on a signal. Increasing bandwidth increases the rate of transmission but also allows more noise to pass, and so the choice of a bandwidth is a trade-off. There are four widely used modem types: the conventional analog dial-up modems, digital subscriber line DSL modems, cable TV modems, wireless modems. Figure 11:12 shows that two ways that modems are commonly used in digital data transmission. In Figure 11:12a, two computers exchange data by speaking through modems. While one modem is transmitting, the other is receiving. Full duplex operation is also possible. In Figure 11:12b, a remote video terminal or personal computer is using a modem to communicate with a large server computer. Modems are also the interference between millions of personal computers and servers that make up the Internet. 11.4 Basic Modem Concepts. Modulation for data communication. The four main types of modulation used in modern modems are frequency shift keying, phase shift keying, quadrature amplitude modulation, orthogonal frequency division multiplexing. In Figure 11:13, it shows the frequency shift keying, wherein A is a binary signal and B is a frequency shift keying signal. These two frequencies are alternately transmitted to create a serial binary data. The resulting signal looks something like shown in Figure 11:13. Both of the frequencies are well within the 300 to 3000 Hz bandwidth normally associated with the phone system. Figure 11:18 illustrates the simplest form of phase shift keying. Binary phase shift keying, or BPSK. During the time that binary 0 occurs, the carrier signal is transmitted with one phase. When a binary 1 occurs, the carrier is transmitted with a 180 degrees phase shift. One commonly used system for doing this is known as quadrature or quadruphase. In QPSK, each pair of successive digital bits in the transmitted word is assigned a particular phase as indicated as Figure 11:24a. Each pair of serial bits, called didbit, is represented by a specific phase. A 90-degree phase shift exists between each pair of bits. Other phase angles can also be used as long as they have 90-degree separation. For example, it is common to use phase shift of 45 degrees, 135 degrees, 225 degrees, and 315 degrees as shown in Figure 11:24. B. The diagram in figure 1124b is called the constellation diagram. It shows the modulation signal in the form of phasors. The length of the narrow or phasors indicates the peak level voltage of the signal, while its angle to the axis is the phase shift. Sometimes the constellation diagram is simplified by showing dots on the axis indicating the location of the phasor arrowhead, as in figure 1124c. This simplifies the diagram, but you should always imagine a phasor drawn from the origin of the axis to each dot. Constellation diagrams are widely used to show phase amplitude modulation schemes. A circuit for producing quadrature phase shift keying is shown in figure 1125. It consists of 2-bit shift register implemented with flip-flops, commonly known as bit splitter. The serial binary data train is shifted through its register, and the bits from two flip-flops are applied to balance modulators. The carrier oscillator is applied to balance modulator 1, and through a 90-degree phase shifter to balance modulator 2. The outputs of the balance modulators are linearly mixed to produce the quadrature phase shift keying signal. Figure 1129 is a constellation diagram of 8QAM signal showing all possible phase and amplitude combinations. The points in the diagram indicate the 8 possible phase amplitude combinations. Note that there are 2 amplitude levels for each phase modulation. Point A shows a carrier amplitude with a phase shift of 225 degrees. It represents 100. Point B shows a higher amplitude and a phase shift of 315. This sine wave represents 011.
In this figure show a block diagram of frequency hooping SS transmitter. The serial binary data to be transmitted is applied to conventional two-tone FSK modulator, and the modulator output is applied to mixer. Also driving the mixer is frequency synthesizer. In the figure, 8 flip-flops in the shift register are clocked by external clock oscillator. The input of the shift register is derived by XORing two or more of flip-flop outputs. The output is taken from the last flip-flop in the register. Changing the number of the flip-flops in the register and which outputs are XORed and feedbacks changes the code sequence. Orthogonal frequency division multiplexing. Another wideband modulation method growing in popularity is called OFDM, also known as multi-carrier modulation. This relative new form of modulation was first proposed in the 1950s, but was not seriously considered until 1980s and early 1990s. Figure shows the concept of OFDM modem. A single serial data stream is divided into the multiple slower but parallel data paths, each of which modulates a separate subcarrier. A simplified version of process is shown in the figure. At the transmitter or modulator, the serial data is modulated. Then a serial to parallel conversion is performed. The inverse path Fourier transform is then implemented. This process produces all the orthogonal subcarriers. The DA converter converts the OFDM signal to analog form and transmits it over the communication medium. Analog telephone modem. The most commonly used modem is one of the connects personal computers to the telephone line. A typical dial-up analog modem consists of both transmitter and receiver sections. Most modern modems are implemented by using digital signal processing technique. Modem operation. The data to be transmitted is stored in the computer's RAM. It is formatted thereby communication software installed with the computer. It is then sent 1 byte at a time to the modem. Most data transfers and operation inside a computer are parallel. But since long-distance data communication is done by using serial binary data, the modem's first job is convert parallel data to serial data. Figure shows the concept of OFDM modem. A single serial data stream is divided into the multiple slower but parallel data paths, each of which modulates a separate subcarrier.
Figure 11-48 shows an ADSL modern all-DMT or OFDM modulation. The modulation is handled by the DSP chip. The digital output of the DSP is converted to analog by D or A converter. The resulting signal is amplified, filtered, and sent to a line driver that applies a high-level signal to the line. The hybrid is a circuit or transformer that permits simultaneous transmit and receive operations on the telephone line. The transformer matches the circuit impedance to the line. Figure 11-49 shows the spectrum of the cable. Television channels extend from 50 MHz or channel 2 up to 550 MHz. In this 500 MHz of bandwidth, up to 83 channels of 6 MHz can be accommodated. Figure 11-50 shows a typical cable modem. It is basically a VHF or UHF receiver connected to the cable for downloads and a modulator or transmitter for uploads. The signal from the cable passes through a duplexer, which is a filter circuit that permits simultaneous transmit and receive operations. The signal is amplified and mixed with a local oscillator signal from the frequency synthesizer to produce an IF signal. The frequency synthesizer selects the cable channel. 11-7 Error detection and correction. When high-speed binary data is transmitted over a communication link, whether it is a cable or radio, errors will occur. These errors are changes in the bit pattern caused by interference, noise, or equipment malfunctions. Such errors will cause incorrect data to be received. To ensure reliable communication, schemes have been developed to detect and correct bit errors. The number of bit errors that occur for a given number of hits transmitted is referred to as the bit error rate or BER. The bit error rate is similar to a probability in that it is the ratio of the number of bit errors to a total number of bits transmitted. 11-8 Protocols. Protocols are rules and procedures used to ensure compatibility between the sender and receiver of serial digital data regardless of the hardware and software being used. They are used to identify the start and end of a message, identify the sender and the receiver, state the number of bytes to the transmitted, state a method of error detection, and for other functions. Various protocols and various levels of protocols are used in data communication.
A circuit for producing quadrature phase shift keying is shown in Figure 1125. It consists of 2-bit shift register implemented with flip-flops, commonly known as bit splitter. The serial binary data train is shifted through its register, and the bits from two flip-flops are applied to balance modulators. The carrier oscillator is applied to balance modulator 1, and through a 90-degree phase shifter to balance modulator 2. The outputs of the balance modulators are linearly mixed to produce the quadrature phase shift keying signal.
The basic process is that information is added or removed as data is transmitted from the one layer to another. Assume that the application's program you are using contains some data that you wish to send to another computer. That data will be transmitted in the form of some kind of serial packet or frame or a sequence of packets.